Waste-to-energy is essentially energy recovery. It involves processing waste material that would otherwise go to landfill in a manner that captures valuable energy or creates marketable products. While WTE is a broad term, the sources highlight several key technologies used to achieve this conversion. 1. Incineration, combustion or mass burn. This is perhaps the oldest and most well-known method. Incineration involves burning waste in the presence of excess air. The goal is to generate heat, which is often used to produce steam and/or electricity. This can also be applied in a combined heat and power setup. Modern plants require sophisticated infrastructure, including flue gas cleaning and dedicated ash handling systems. 2. Gasification. This method uses controlled conditions to process the waste. Gasification is characterized by the partial oxidation of waste, meaning it uses limited oxygen or air. The primary output is synthetic gas, a mixture typically containing carbon monoxide, hydrogen, and carbon dioxide, among other components. This synthetic gas must be cleaned and can then be utilized for combustion, directed to a turbine/generator, or chemically converted into specialized fuels or chemicals. 3. Pyrolysis. This technology forms the basis of the demonstration project we will examine today. Pyrolysis involves the decomposition of waste solely by heat. Crucially, this process occurs in the absence or very low presence of oxygen. Depending on the precise thermal conditions, pyrolysis produces three main product streams: pyrolysis oil or bio-oil, char, and gases. Challenges and trade-offs in advanced waste-to-energy. While gasification and pyrolysis are attractive in models, they present notable practical challenges. Costs. They generally require high capital and operational expenditures, particularly associated with advanced reactor designs, synthetic gas conditioning, and complex gas cleaning processes. Feedstock handling. Waste is heterogeneous. This necessitates significant pre-treatment steps, such as sorting, drying, and size classification, making process control difficult. Technical issues. Issues like tar formation in both gasification and pyrolysis, along with managing the residues like char and ash, require specialized handling. Scale and regulation. Small plants often struggle to be cost-effective or efficient. Furthermore, regulatory and permitting challenges exist due to concerns over local pollution, public acceptance, and the safe handling of residual materials like fly ash. Utilizing the energy and products produced. When we discuss the energy produced, especially in advanced thermal processes like pyrolysis, we are talking about valuable product streams that replace fossil fuels and carbon-intensive materials. The Renergy project specifically generates four key outputs. 1. Bio-oil, crude pyrolysis oil. This is the liquid product. Industrial heat replacement. Bio-oil can be burned directly in industrial boilers to provide process heat, potentially replacing traditional fossil fuels such as diesel or fuel oil. Industry focus. In Western Australia, industries with high thermal energy demands, such as cement, mining, and agriculture processing, are identified as prime candidates for using this bio-oil. While refining bio-oil into transport fuels is possible, the Collie project currently focuses on industrial heating. 2. Biochar, solid carbonaceous residue. Biochar is a highly valuable solid product. Agricultural use. Its main purpose is as a soil amendment, significantly improving soil fertility, enhancing water retention, and potentially reducing the need for chemical fertilizers. Carbon sequestration. Biochar is stable carbon. When placed back into the soil, it effectively locks away carbon long-term. This sequestration is why the project has the potential for a negative emissions profile, meaning it removes CO2 from the atmosphere compared to allowing the biomass to decompose. Other applications. Biochar can also be used as an animal feed supplement, improving digestion and reducing livestock methane, or as carbon materials for filtration or activated carbon production. It can also serve as a filler or substitute in cement and building materials. 3. Wood vinegar, pyroligneous acid. This is a condensable liquid product. Wood vinegar has established commercial value in agricultural and horticultural markets. It is used as a natural soil enhancer, fertilizer, and pesticide. 4. Process energy, self-consumption. Not all gases condense into bio-oil. The non-condensable gases, including CO, H2, and methane fractions, can be reburned on-site to supply the necessary process heat for the pyrolysis reactor itself and to run the integrated drying equipment. This utilization of off-gases helps the plant achieve greater energy self-sufficiency. The Renergy Pyrolysis Project in Collie, Western Australia. The Renergy Pyrolysis Project serves as an important pre-commercial demonstration plant for this advanced WTE technology. The plant is located in Collie, Western Australia, co-located specifically at the Shire of Collie's landfill site. It is designed to test small modular-scale EFW economics. The demonstration capacity is small, approximately 1.5 tons per hour of dry feed throughput. Funding. The total project cost is significant, around 9.4 million Australian dollars, with substantial financial backing from the Australian Renewable Energy Agency, contributing about $3.9 million, and the WA state government's Collie Futures Industry Development Fund, contributing about $2 million. Feedstock and purpose. The plant is specifically designed to handle mixed input to divert waste from landfills. It utilizes approximately 4,000 tons per year of municipal solid waste that would otherwise be landfilled. Additionally, it processes about 8,000 tons per year of forestry and agricultural waste biomass. Its purpose is to convert these diverse feedstock streams into bio-oil, biochar, and wood vinegar. The technology. Grinding pyrolysis and integrated drying Renergy employs a proprietary process called grinding pyrolysis, which integrates two key functions. 1. Simultaneous grinding and pyrolysis. Unlike traditional systems that require very uniform input, grinding pyrolysis allows large or heterogeneous waste particles to be mechanically comminuted ground while thermal processing is underway. This grinding action is critical because it exposes more surface area to the heat, helps to avoid char buildup on the surface of the particles, and results in a more uniform and rapid pyrolysis process. 2. Key technical advantages. Wide feedstock tolerance. This system can accept a wider range of biomass and waste types, tolerating variation in particle sizes, from microscale up to a few centimeters, and varying levels of moisture and heterogeneity, reducing the need for extensive pre-processing. Minimal carrier gas. Many pyrolysis systems rely on inert carrier gases, like nitrogen. Renergy's design requires little to no carrier gas, which improves energy efficiency, simplifies gas handling, and aids in the condensation of the valuable bio-oil. Indirect drying integration. Moisture content severely lowers pyrolysis efficiency because energy must be expended to evaporate water. Renergy integrates patented drying technologies to reduce the moisture content either before or simultaneously during the pyrolysis stage, enhancing net energy yield. Environmental and carbon impacts. The project provides significant environmental benefits. By diverting waste from landfill and replacing fossil fuel use, the plant is estimated to avoid approximately 18,000 tons of CO2e emissions annually. Landfill diversion is important as it reduces significant methane emissions, a potent greenhouse gas. As noted, the production and sequestration of stable biochar provides the plant with the potential for negative emissions. The plant secured works approval under Western Australia's Environmental Protection Act, though amendments were necessary concerning specific emissions and discharges. In summary, waste-to-energy offers essential pathways, like incineration, gasification, and pyrolysis, to manage waste while recovering resources. The Renergi project in Collie provides a valuable case study in advanced pyrolysis, demonstrating how waste can be converted not just into electricity, but into high-value products. Bio-oil to replace fossil fuels in heavy industry, biochar to lock away carbon and enhance agriculture, and wood vinegar for specialized farming markets. While challenges in feedstock handling and costs remain, the modular design and focus on negative emissions potential highlight the future role of projects like Collie in sustainable waste management and regional resource recovery.